Hello, welcome back. This is Dr. Stutzman, and today we're going to talk about some tests, more tests that tell if a series is convergent or not, the comparison and limit comparison tests. So today we're going to talk about two tests that let us compare a new series to series we already know about. So we're going to look at, in this series, you might have one of these series you might know about, A sub n. And what can we tell about a series that is smaller than it? Do we know if A sub n converges? Do we know if B sub n also converges? Or if A sub n diverges, does the sum of B sub n also diverge? So let's compare these two series, 1 over n squared, which we know some things about. This is a P series, and it converges because it's a P series where P is greater than 1. But here's a series that's not a P series, but it looks a lot like it. Does that also converge? Well, if you look at those two series, which of those two series have larger terms? Which of the terms are always larger? So I know that n squared is smaller than n squared plus 8. So if I add 8 to a number, it makes it bigger. So this guy has a smaller denominator than this one does. And the numerators are the same. So if you have a smaller denominator, you're dividing by a smaller term, then that means that 1 over n squared is bigger than 1 over n squared plus 8. Whenever your denominator is smaller and the numerator is the same, then your fraction has to be bigger. So 1 over n squared is larger, and it also converges. What can we conclude about 1 over n squared plus 8? Well, since if this is a larger series, which is 1 over n squared, and that goes to a number, this goes to a finite number. So all of the yellow a sub n's, 1 over n squared, goes to a finite number. The bottom one can't shoot off to infinity because it's smaller, because each of the terms are smaller. So 1 over n squared plus 8 must also be finite. So 1 over n squared plus 8 must also converge because it's smaller than another series that converges. So in general, here's the comparison test, also known as the direct comparison test, because we're comparing two series to each other and telling to see which one directly is bigger or smaller than the other. So I have two series, A sub n sub B sub n. This is the larger series. A sub n is the larger series, and B sub n is the smaller series. If the larger converges, if the A sub n's converge, then the smaller one has to also converge because it's being clamped down by the larger series. And if the smaller series diverges, then the smaller series is shooting off to infinity. Then the larger series also has to diverge. So here's an example. Does the sum of 2 over n times n plus 5 converge or diverge using the comparison tests? So what series do we want to compare it to? Well, I know what 1 over n does, and 1 over n diverges, but we don't really have 1 over n. We have something that looks like 1 over n squared. And I know that 1 over n squared, the sum is n equals 2 to infinity. This one converges because once again, from P series. So what does this series, the sum of 2 over n times n plus 5, have to do with that? Well, let's do some simplifying. First, I can pull the constant out because multiplying a number by a constant is not going to change whether or not it converges or diverges, because that's just a sum of numbers. I can just use the distributive property and pull the 2 out. And I'm also going to distribute n times n plus 5 and get 1 over n plus 5n. Well, 1 over n squared plus 5n is, let's just focus on that part. N equals 2 to infinity of 1 over n squared plus 5n. That is smaller than the sum from n equals 2 to infinity of 1 over n squared, because the denominator is bigger in n squared plus 5n. So that means that the fraction, which is the reciprocal, is smaller than 1 over n squared. So this one converges by p series. 1 over n squared converges by p series. And p is equal to 2, which is bigger than 1. So that means that the smaller series also converges. And if I multiply it by 2, it still converges because I'm multiplying by a constant. So 2 over n times n plus 5 converges by the comparison test. All right, here's another one. Natural log of n over n, converge or diverge using the comparison test. Well, I don't see any powers of n, but I know that the series of 1 over n diverges, because that is a p series when p equals 1. This is also known as the harmonic series. So what does natural log of n over n have to do with 1 over n? Well, the denominators are the same between these two. And natural log of n, as long as n is bigger than 2, is going to be a, well, natural log of 2 is a number that's smaller than 1. But eventually, as n goes to infinity, the terms get bigger. So I'm going to simplify this a little bit. I want to make sure that this is always bigger than that one. So let's do the sum. Let's do natural log of 2 over 2 plus the sum from n equals 3 to infinity of the natural log of n over n. Natural log of anything bigger than e is bigger than 1 as long as n is bigger than e. So let's compare it. So that means that this series, the series from n equals 3 to infinity of natural log of n over n is bigger than the sum from 3 to infinity of 1 over n. And this diverges because it is harmonic in a p series where p equals 1. So that means the larger series has to also diverge. It can't be, it's not being, the smaller series is shooting off to infinity, so the larger series also has to shoot to infinity. And if I just add a constant natural log of 2 over 2 to it, that's not going to change whether or not it converges or not. Now, let's do another test. And this time, we don't have it's harder for us to compare to a larger, hard to clamp down a series that we're trying to show converges. So 1 over n squared and 1 over n squared minus 8, they're related, but the comparison doesn't help. The reason is because which is the smaller series? 1 over n squared is smaller than 1 over n squared minus 8, because n squared is bigger than n squared minus 8. So the reciprocal 1 over n squared has to be smaller than 1 over n squared minus 8. So here is 1 over n squared, and the bigger series is 1 over n squared minus 8. And just because the smaller series converges doesn't help us with the larger series because the larger series is not being clamped down. So we can't tell if something's convergent that's bigger than a convergent series. So instead, let's compare it a different way. Let's see, eventually, as n goes to infinity, 1 over n squared and 1 over n squared minus 8. 1 over n squared is always smaller than 1 over n squared minus 8, but they're eventually, the 8 is going to be kind of meaningless. They're going to be very close to each other. They're always going to be, one's going to be like basically the same factor of the other. So in the limit comparison test, we're going to compare two series where they're always positive numbers, or non-negative at least, for every number at after some point. Suppose that the limit of the terms, the ratio of the terms is some constant, has to be not zero. So eventually the terms are a constant multiple of each other. So they're going to work at like in lockstep with each other. So if they always approach a constant, then the two series either both converge or both diverge. They'll work the same way. So objective is find a series closely related that we know the convergence of. So back to n squared minus 8. Does it converge or diverge using the limit comparison test? We're going to compare to 1 over n squared. Which we know converges because it's the p series, and p equals 2. So we'll call this series a sub n. We'll call this series a series of b sub n. What is the limit as n goes to infinity of a sub n over b sub n? That is the limit as n goes to infinity of a sub n is 1 over n squared minus 8. And I want to divide that by 1 over n squared. Let's flip the fraction on the bottom, which is n squared over n squared minus 8. And that limit is 1 because that is a limit of a rational function where the coefficients, where they have the same degree. So it's going to be the ratio of the leading coefficients, which is 1. So because both series, because this is a number that is greater than 0 and it's finite, it's a non-zero number, both series are positive as long as n is bigger than 3. 3 being because 3 squared minus 8 is a positive number. So both series do the same thing. Converge or diverge together. And because 1 over n squared converges, both series converges. Both series converge. All right, let's do another example. This is an example we did before, limit comparison test. I'm not going to worry whether or not this is bigger or smaller than another series, but it looks like 1 over n squared. There's an extra 2, but we'll just compare. This will be our a sub n terms. These are our b sub n terms from n equals 2 to infinity. Let's take the limit as n goes to infinity of the ratio of the terms, which is the limit as n goes to infinity of 2 over n times n plus 5 divided by b sub n. I'm going to flip b sub n over. So that's a sub n divided by b sub n. Do some simplifying. Limit as n goes to infinity of 2n squared. The denominator, if I multiply it out, is n squared plus 5. Once again, this is a rational function of the same degree. So it'll be the ratio of the leading coefficients, 2 and 1. So that limit is equal to 2, which is a constant that is, it is a finite number that is greater than 0 and less than infinity. So they do the same thing. And so because the similar series 1 over n squared converges by p series, then the sum of the other series, 2 over n times n plus 5, also converges by the limit comparison test. Some examples to try yourself. Use the sum of 3 to the n over 5 to the n plus 2 using the comparison test, which we have to compare to a larger or smaller series, depending if you're trying to tell if it's convergent or not. Or the limit comparison test, where the terms are a constant multiple of each other, or as n goes to infinity. And we're going to check with both of those. So what can we compare it to? Well, 3 sub n over 5, 3 to the n over 5 to the n plus 2, the 2 becomes kind of insignificant. That looks like the sum from n equals 2 to infinity of 3 to the n over 5 to the n. And they're both going to the same power. So we compare that to the sum from n equals 2 to infinity of 3/5 to the nth power. So compare to this series. And I'm not going to tell you why, but you should know why does this series converge? Why does this sum of 3/5 to the n converge? And after your comparisons, you should also be able to show that the sum of the related series 3 to the n over 5 to the n plus 2 also converges. All right. Thank you for your attention. And if you have any more questions, come look for one of your teachers. Thank you.